This is the first one. Now, flying turkeys tomorrow, I figured I'd do all my handouts tonight. Okay, so this is the first one. So let's talk about motion on a curve. So first of all, there's two kinds of curves. There's flat curves, like when you go around, like out here at the corner, at the co-op, when you go around the sort of little exit there to go down, what is that, First Street? Yeah. So it's like a curve, right? It's kind of like that side little thing. Yeah. Yep. Right? Okay, so that's a flat curve. And then there's banked curves. Now, if you watch NASCAR or anything like that, you know that they go in the big circle, right? And they've got the banks, right? Most highway curves are slightly banked as well. You just don't realize it. Okay? Because you are traveling at a pretty good speed. Okay, so we're going to talk about those as well. If you think about like going up onto on-ramps and stuff like that, there's a bank to it as well, right? Okay, so the net force on a curve, traveling around a curve, is the centripetal force, Fc, which is equal to mv squared over r. And it's directed toward the center of the curve. For a level curve, the centripetal force will be supplied by the friction force between the tires and the rotor. So that's a key point right there. For a level curve, the centripetal force is simply the friction force, right? As you go around the curve, it's friction that pushes you towards the center. And a banked curve can supply the centripetal force by the normal force and the weight without relying on friction. So it's a different scenario. So the first one we're going to talk about is level curves. That's the easy. So if you imagine there's a couple of drawings here of a car. So this is obviously like from a bird, up the top side view, a drone view, if you will. So as this car goes around the corner, it's the centripetal force directed towards the center, and that centripetal force is provided by the friction, right? And you can see the velocity is moving the car forward. Friction is pushing it towards the center, right? And here's the sort of behind the car view, right? And you've got the normal force up, and you've got the weight force down, and you've got Fc, which is equal to Ff. Okay, so again, for a level curve, the centripetal force will be supplied by the friction force between the tires and the rotor. So here, we're going to jump right into an example. Okay? We're going to jump right into an example. What must be the coefficient of friction between, is this on the front page for you guys? What must be the coefficient of friction? So we're looking for the mu value between the tires and the level roadway to allow a car to make a curve of radius 350 meters at a speed of 80 kilometers an hour. For a level curve, the force of friction is the only horizontal force and provides the centripetal force. This can be seen from the free body diagram, which I hope is on the next page. Okay, so on the next page, again, on the left-hand side here, this is the top-down view. Right, see that? We converted our 80 kilometers per hour. We divided by 3.6, and we got 22.2. That's where that comes from. So the velocity is 22.2. The radius of curvature is 350 meters. So in other words, if you were to like put there's some magical point there in the center, and if you were like string a string that's 350 meters long, it would exactly go along that curve, right? That's what the radius of curvature is. So it doesn't have to be, when we say radius, it doesn't have to necessarily be for an entire circle. Because going around a curve is circular motion, you just don't complete the circle. Does that make sense?
Yes.
Hey, what's going on? The net force must be horizontal, pointing towards the center of the circle, and only the friction force is able to provide it. So the normal force and the weight simply cancel each other out. Calculations are easier if we express it into meters per second. Now we calculate the necessary centripetal force. And now, okay, so we're going to calculate the necessary centripetal force. So let's write here. Maybe I have it. Do I have it kind of like a thing that I can click? No, I don't. That would be so good. I should. Fc is equal to mv squared over r. Do you have this?
Yeah.
So you have it and I don't.
Yeah. Well, what the heck?
Who set this nonsense up? Again, rhetorical question. Okay, so the mass is... Oh, now we don't have the mass of the car, do we?
What's the mass of the car?
Okay, now what are you going to do when you don't have the mass of the car? Well, we're just going to leave the letter m in there, and we're going to hope that it's going to cancel.
But it didn't.
We're going to hope. Hang on. So we got mv squared is 22.2 squared, and that's an r underneath there, right? Mv squared over r, so we got 350. So the centripetal force is 1.41 m. What the heck does that mean? 1.41 times the mass. So let's just say the mass was 1,000. It'd be like 410 newtons, I guess, right? So it's just m. We don't know what the mass is. Now, think about this. Does it matter? Like, if you've got a really light car going around the curve, or you got a really heavy car, should that matter? Like, should you be able to go faster in a heavy car or slow? Like,
Oh, no,
like,
mass doesn't matter.
the mass, you would think that for highway, the mass should not matter, right?
Yeah.
Okay, so let's just see here. So we got 1.41 m. Now, the normal force is going to be mass times gravity, which again we don't have. So it's 9.8 times m, right? Okay, so it says here now, for this flat curve, the centripetal force is applied by the friction force. And friction force is FF, right? Now, this formula right here, have you seen this one before?
No.
Well, you have. This one here is just mu equals FF over Fn, right? Which is just FF is equal to mu Fn. That's all it is, right? So, mu Fn, now Fn is equal to 9.8 m. So we're going to stick that in there, right? So the friction force, which is mu times 9.8 times m, must equal my centripetal force, which we've given to be 1.41 m. And guess what? The m's cancel. The m's cancel. So you get mu equals 1.41, which you guys probably have and I don't for some silly reason. You get a mu value of 0.141, which means that if the frictional coefficient is 0.141, then you can go around the curve. There's enough friction to do what? To keep you on the curve, to push you towards the center. What if the mu value is 0.2?
You're still good.
You're still good? How come?
Because that's the minimum.
That's the minimum, right? If friction is more, if it's rougher, does it mean that it's going to like push you right into the center of the surface and you're going to crash and there's a tree in the middle?
Yeah.
Okay, so
No.
Depends how hard you turn.
if that's minimum, like if it was 0.1, what would happen?
What would happen? What happens if there's not enough friction as you were on a curve?
You
Slide out.
do a good drift.
You drift, exactly. Get my drift?
Got it. I caught it.
Of course, any coefficient of friction greater than 0.141 will keep the car from slipping. This is the, as Riley said, this is the minimum value for mu. Notice that the force of friction is perpendicular to the velocity, but it is still in the direction necessary to oppose the motion that would occur without friction. The car will slide away from the center to the right in this diagram if it encounters a patch of low friction surface like ice or oil. Therefore, the friction force is directed towards the center. Notice too that we are dealing with static friction, which is friction at rest. The piece of tire in contact with the road is momentarily at rest with respect to the road. The force of static friction is somewhat greater than the force provided by kinetic friction if the tires start to skid. Once you start to skid, it's hard to stop because kinetic friction is less than. Okay, now we're going to come up with some kind of crazy formula here.
One of these bloody formulas.
Yeah. Okay, so what is the maximum speed that a 1,500 kilogram car can round a level curve if the radius of the curve is 100 and the frictional coefficient is 0.65? So let's start off by realizing, okay, this is an unbanked curve, right? Which means that the centripetal force is provided by the friction force. So let's start with that piece of thinking. That is sort of setting up our thought process. The frictional force is providing the centripetal force. And we know that FF is equal to mu Fn, right? So that's going to be, now Fn is really m times g, right? Right? Weight force, normal force, right? Okay, so this is going to be mu mg, or 0.65. Now I thought the mass didn't matter. Well, let's plug it in and we'll see what happens. 1,500 times 9.8. So 0.65 times 1500 times 9.8, and you get a frictional force of 9555 newtons. The maximum frictional force is 9,555 newtons. Is it negative? Well, remember the 9.8 just means directed down, right? But Fn is actually directed up, right? So this 1500 times the 9.8 numerically is just whatever those two numbers are together, right? The negative and negative 9.8 just means that it's down. So does it matter here? No, and certainly, and the FF is actually like this way, right? So the negativeness of that minus 9.8 is irrelevant. Well, you should watch. Okay, so that FF is providing that is our centripetal force, FC, which I can't apparently write. FC mv squared over r. So 9555. The mass is 1500. We're solving for V. And my radius is 100.
What's the uppercase R?
Because I'm tending to put R now as big uppercase. The big R, little r don't matter.
Well, this one.
I know, I was bad. I screwed up every year trying to. Okay, can we solve this for V? V is going to be equal to, how do I get rid of the divide by 100? Multiply, so that's going to be 100 times 9555. And how do I get rid of the divide by 1500? Or sorry, the multiply by, divide. And because I got a square root, I'm going to have to do that whole thing, right? Now, I realize that sometimes the calculator gives you some issues. So you would go 100 times 9555 and divide by 1500. You'd have to go equals. And then you'd have to take the square root of that. And you get something like 25.2. Whoa. I can only go 25 kilometers an hour around this corner? Are you sure? Yep, meters per second. Okay, because that's the standard unit. So that 25.2 is meters per second. And of course, you're going to have to multiply by 3.6 because nobody knows how fast that is. And you get 90.9 kilometers per hour. If you go faster than 90.9, you're going to start sliding out.
What is this?
And it does, now hang on, that frictional coefficient of 0.65 is dependent upon the two surfaces, right? So if I've got like really lousy tires, and you've got super duper tires, your coefficient is going to be a little bit more than mine. Right? Okay. Did the mass matter at all here? Well, here we multiplied, so that 9555 has a 1500 multiplied in, right? But then over here, I took that 9555 and I divided by 1500. So yes, I did take it out. So it's in the question, but it's irrelevant.
Why don't we just take it out?
You can. It's just that you'd have to, here you'd have 0.65 times 9.8 m, and then over here you'd have another m, and you'd have to do that whole canceling thing, and it's probably better this way, right? Okay. But I do want you to see that the mass doesn't matter. So when you see corners like, is that right? Oh yeah, I think you're right. Valley River Highway. You can go down to 90 there? 70?
The whole highway's 90.
Right, the big corner there, by your house,
Yeah,
right?
it's still 100 there.
It's still 100?
And then once you go over one,
Is 90.
The whole highway is 90. It's just everyone goes 100.
yeah, and then once you go
I go 106.
right before Valley River, it goes down
My
to
date doesn't get to
70.
that one.
Okay. So there are some curves. I know there's a curve in the park where like the park limit is 80, right? And then there's that one little curve where it's a single that goes down to 70, right?
Yeah.
So it would be based on something like this. Now, would they let you, like, would they just put up, like, if it's 90, I'll get you a picture. If they come up with 90.9, do you think that they're going to put up a sign that says go 90?
Mm-hmm.
No, because they don't like, no guys like Brett are going to do 160. Okay, so they probably build in quite a range of safety. And that's based on
Crashes.
Yeah, and that's also based on frictional coefficient, good conditions, right? So if it's icy, then yeah, you gotta slow down, and that's why.
The turn off the, when you do this, going down the gravel road, it's like on the gravel road, and you do a turn, one way, so the truck is different. It's like the gravel road near there, it's like a turn, it's like a turn on the gravel road, and they turn like really, it's in turn straight out, because it's not just a sharp turn.
Okay, so that was unbanked curves. Unbanked curves are relatively easy. Go ahead, Jared. Got it.
I was just gonna ask, does FF equal FC in every case, or would it be different?
No, on a flat curve, unbanked curve, the centrifugal force is provided by the friction force. So FC is equal to FF on all unbanked curves. Okay, now when it's banked, it's a whole other different thing. So, you should have this. I think you might have to go one more page forward. Got it. Put it away. I think you gotta go one more page forward, all right? Yeah. Okay, I think I was just saying this page. I put the example beforehand. Okay, so question here. Civil engineers generally bank curves on roads in such a manner that a car going around the curve at the recommended speed does not have to rely on friction between its tires and road surface in order around the curve. So engineers will actually bank it so that when it is icy and there's less friction, you can still get around the corner. How do they do that? By banking the curve. Suppose the radius of curvature on a given curve is 60 and the recommended speed is only 40. At what angle should the curve be banked? So how much incline should we have? Okay, now here's where it gets complicated, and I have to stop for a second and gather my thoughts. So this is like a cross section. We're looking at the back of the car here, okay? I guess it could be the front as well. Okay, there's the tail lights. Makes the car look angry. There's the tail lights, right? Now we know that the weight force is directed down, mg, and this one here is really Fn, the normal force. Remember all this stuff, like things on ramps? Remember that? Right? You got down, you got Fd, all that good stuff. Okay, so consider a car mass m going around the curve. The car's weight mg acts vertically downward. The road surface exerts an upward normal force F on the car. Now that really should be F and the vertical component of the reaction must balance the downward weight of the car. So now if you take this, if I draw this triangle right in here, that right there is this picture. Does that make sense? Did you see what I did there? Okay. See this right here in blue? That's this big one right there. That's F normal. Okay? And now if I finish this little guy right here, that's the rest of this triangle over here. Right? That is this one. Okay?
Wait, why are you switching to FN now?
This was Fn here. Yeah, it's the normal force, right? Okay, now remember, from the ramps, this angle theta here would be equal to that one in there, right? Remember that, Johnny? Okay, so the weight which is down, this is mg, this guy and the F cos theta have to be balanced. Is that what you're saying, Tara? They have to be balanced, right? How did I get F cos theta here? Well, this is my theta. This side here is adjacent, right? So it's F times the cosine of theta is going to give me this here. Don't worry, I'm going to give you a formula at the end. We'll work towards the formula. This is the formula derivation. You just didn't realize it. The horizontal component of the reaction, F sine theta, this one here, acts towards the center of the curvature of the road. So this guy here is really providing the centripetal force. It's almost equivalent to Fd. Almost. It's the horizontal component of the normal force. I have to be careful here how I say this. The The horizontal component of the reaction, F sine theta, acts towards the center of the curvature of the road. This component provides the force towards the center of the curvature, which the car experiences as it rounds the curves. In other words, and here's where things get crazy, because I always have it blanked out. I gotta make sure I don't screw this up. In other words, F sine theta is equal to, do you have this on your sheet?
Yeah, that's why it's.
But then we don't have what's under.
F sine theta is equal to mv squared over r. Okay, now from the diagram, from this right here, F sine theta, now, you remember identities in pre-calc? Remember that? Trig identities? Taryn just finished it? Tan theta is equal to? Sine theta over cos theta, right? You don't have to know this. You don't have to know this. But think about, it's a equivalent tan theta. What is the tan theta is? Opposite over adjacent. What's opposite of the angle? F sine theta. And what's adjacent to the angle? F cos theta. Okay, which means then that F sine theta, and I never leave myself enough room, F sine theta. If I'm rearranging this to F sine theta, I'm going to get F cos theta tan theta. You see what I did there? I took this bit down here and I multiplied it up there, right? Okay. So F sine theta is equal to F cos theta tan theta. No, we're doing a derivation here. Don't worry, I'll put it in a box for you when we're done. But F sine theta was equal to mv squared over r. So, mv squared over r is equal to, now what's F cos theta? mg. So we get tan theta. And now what happens? Are you surprised that the m's cancel? You shouldn't be. The mass of the car shouldn't matter. And so you end up with, can I go up over to the right here? V squared over r is equal to g tan theta, which we commonly rewrite as tan theta for a banked curve is equal to v squared over rg. And that, my friends, is the formula for a banked curve. Okay, we just derived it. Tan theta is equal to v squared over rg, where theta is the angle of the bank, v is the velocity or speed, r is the radius of the curve, and g is simply the 9.8.
Is that the only formula we need to know?
That's the only one you need to know for bank curves. Now this is only if the curve is frictionless. So there's actually more to it. And when you add in friction, it actually gets quite complicated. There's a question in a problem pack somewhere. It's really hard. Don't worry about it. It's not going to be on the test. We're going to deal with frictionless banked curves and friction-full unbanked curves. Note that if the car attempts to round the curve at the wrong speed, then, and the difference has to be made up by a sideways friction force exerted by the car's tires and the road surface. Unfortunately, this does not always work, especially if the road surface is wet. Okay? Obviously. So here is the example. It is a banked curve. So yeah, you have to go back in time, or back in page. A race car travels along a banked curve at a speed of 120 kilometers an hour. It doesn't depend on the force of friction to keep it on the track. If the turn is banked at an angle of 25, Riley, what are you doing? What is the radius of rotation? So imagine a race car track engineer who's designing a track, and they know that the cars are going to be traveling a maximum of 120, right? And they can bank at 25 degrees. What is the radius of rotation? Maybe they have to figure out how much land they need to buy so that they can build this track. That kind of thing. What is the radius of rotation? So we are solving for r. So the first step is to take that 120 divide by 3.6, and then the answer's right there. It's in the diagram. 33.3. Okay, so we are solving for r. What was that new formula? Tan theta is equal to? Right. V squared over rg. So tan 25 velocity squared, so 33.3 squared over r times 9.8. How do I solve that for r? Yes, you can tell me. I'll keep the secret. The r has to go up here, right? The r and the tan 25 have to change. So r is going to be 33.3 squared divided by 9.8 tan 25. Now, one of the main problems with questions like this, most of the time your divide bys, your denominator is going to be a single thing, right? But you have to divide by the whole thing. Okay, so I strongly suggest you put brackets there. Okay, so on your calculator, you're going to go, get your calculator out, let's do it together. So you're going to go 33.3 squared. You can go equals now if you want. And then you're going to divide by left bracket, 9.8 times. Now your calculator depends whether it's tan 25 or 25 tan. That's up to whatever your calculator does. Mine's tan 25. And then you have to go right bracket to close that. And then you go equals. And you should get 242.7. 242.7 meters. Okay? One step. Yep. That's it. It's once you know the formula, right? No, they get a little bit harder. There are some questions in the problem pack where instead of a car on a curb, it's a plane. So what provides the normal force? What provides the up force on a plane? It's the air, the lift force, right? So there's a couple questions like that.
Oh, it does so much.
Of course it does.
No.
Oh, no? Okay. So that's all I have for that. Now let me put this away here first.
That's a different number.
Let me put this away so I don't lose it. Now you should have a few other packages of things, right?
There.
Okay, so flying pig, just store that in your binder for tomorrow. Okay, that's tomorrow's lab. It's a group lab. I only have one flying pig. We will do it as a big class learning pig. Well, it's a lab, but you watch me do it. And you record it out. There is one question on it. It's a relatively easy question, but if I don't do the actual lab, we won't get it. Okay, so I'm just telling you what the rest of these things are. So hang on to that for tomorrow. I located this. This is probably the worst sheet that I can find because all there is answers. There's no solutions. There's no link. But if you want more circular motion questions, they're here. If you need more. Okay? There is a pre-test on banked and unbanked curves. If you want to try it, super easy, really, right? So if you want to do that today, that's fine. I strongly suggest, Taryn, you took that one back, right? Pre-test number 1, if you get them to me, I'll quickly mark them, like on the other UCM stuff. I've given you the rest of this period. You got almost a half an hour. Use it. Tomorrow we'll do flying pig. You're going to get the second half as well. And then you got Wednesday and Thursday to get ready for Friday. Oh yeah, that's right. Thanks, Josh. There is also, on the one you just did, Josh is right. There's also on the back of the thing I just gave you today, there are questions on unbanked curves and banked curves as well that are for practice. You'll notice that there's some on the back. 7 and 8 are crazy hard. I haven't had anyone yet figure them out. I have answers, I got it on the textbook. I've never had anyone figure them out. Well,
Why didn't you point at me? I'm
good
on
luck.
I'm
I
on
have
it.
figured them out myself.
Hold on, Riley.
And I think there's no solution link there. I'll just put it up. I know I have it. That is all I have to say.
The question 7.